Hello everyone, my name is Nicholas Jeffrey. I'm a PhD student at the University of Oviedo, and I'm here to talk to you today about intrusion detection and prevention in the industrial Internet of Things. So the things I'm going to talk to you about today, I'll start with a brief introduction. We'll move on to the research rationale, or why I'm working on this particular topic, the current state of the art, different intrusion detection strategies, some of the challenges that exist in this field, future works that I'll be working on, and then I'll open the floor to comments. So, what is the industrial Internet of Things? Is it just a bigger, stronger, faster Internet of Things, like we have at home with smart lights and smart fridges? It's not a terrible description, but a more accurate description would be integrated systems that combine cyber components or software components with physical components, like sensors and actuators, like you'll find in industrial processes. Another good way to think of the industrial Internet of Things, or the IIoT, is a merging of information technology networks with operational technology networks. And a lot of the things I'm going to be talking about today are the challenges associated with merging those two distinct or different types of technologies. One thing you might hear a lot in industry, specifically from the industrial side, is SCADA meets the internet, or industrial control systems or industrial control processes getting connected to the internet. And there's a number of terms you might hear thrown around with varying degrees of overlap. The IIoT is also sometimes referred to as Industry 4.0, cyber physical systems, smart anything, smart cities, smart power grid, smart water, smart traffic control systems, etc. So why is this an interesting field of research? It's very rapidly evolving. There's a tremendous number of research opportunities in this field. And if anyone has watched the news over the last 5 years, you'll see there's constantly issues in the news about critical national infrastructure being attacked by malicious actors, power grids, water treatment plants, railway networks, etc. The first large-scale attack of this type happened way back in 2005. It was an attack on the processing facilities in a uranium enrichment plant. And that kind of kicked off an arms race between the operators of these industrial Internet of Things, or cyber physical systems, or industrial control systems, and malicious actors that were attacking them for financial, political, etc., different reasons. So attacks like that have really only accelerated as more and more of these systems do get connected to the internet, and those have got pretty significant economic impacts and impacts on life safety, quality of life. Perhaps the most recent example would be attacks on the Ukraine power grid, specifically in the wintertime, that led to hundreds of thousands of people being without heating in the winter. So what is the current state of intrusion detection for industrial environments? A lot of people think that intrusion detection is a solved problem. We already have everything we need for intrusion detection, and maybe that's true for information technology networks. On traditional IT computer networks, we already have perimeter firewalls that do deep packet inspection, any of the choke points between different networks. We have web application firewalls that make sure we don't have any malicious URLs attacking any of our web-managed devices. We have endpoint detection and response on all of our endpoints. And even if anything does get through all of those different layers of defenses, we have SIEM and SOAR products, security information and event management, that tracks and correlates all of the traffic looking for malicious patterns on our network, and to a lesser extent, automated response with SOAR, security orchestration and automated response that fixes or deals with or addresses security or intrusion incidents in real time. And maybe the people that say that's a solved problem are correct from a certain perspective, because it is largely a solved problem for IT networks. The organizations that have trouble with these issues, it's not because they don't have the tools at their disposal, it's that they're not using the tools that exist. That's not really the case on the operational technology side. Those tools, if they even exist at all for operational technology networks, they lag significantly behind the information technology network environments. And a lot of that is for historical reasons and for inertia. Historically, these operational technology networks have been on isolated, fully trusted networks, which allowed them to maybe not worry about any malicious actors because they were air-gapped. Only trusted actors were permitted on the network, and they kind of maybe pretended that the human operators never made mistakes and never accidentally did bring in malware from the outside on a thumb drive, accidentally connect a control system to a public network, etc. So there may have been a lot of wishful thinking in the past, but that's largely become a wake-up call as organizations merge or connect their operational technology networks with their informational technology networks. And some of those differing historical priorities are starting to cause a lot of trouble for organizations. And a lot of that is because of differing priorities. So when we're talking about information security in general, all information security rests on three fundamental pillars of confidentiality, integrity, and availability. And IT networks and operational technology networks really have similar goals, but their priorities are opposites. Traditional IT networks have really prioritized confidentiality first, so password protection, making sure only authorized people get access to resources, followed by integrity, making sure unauthorized personnel aren't able to make changes to production data. And that would include things like ransomware attacks, crypto locker viruses, that sort of thing, with availability being still important in IT networks, but maybe the third priority. And this is going to include making sure these systems are always available. So for traditional IT networks, we're talking about data centers with redundant power, redundant cooling, redundant networks, etc. Operational technology networks, because historically they've been isolated, they've been air-gapped, availability was really the only thing that was considered. Because the networks were not connected to any malicious networks, confidentiality was just sort of assumed to have already been in place. And since everyone on the operational technology network was already trusted, integrity wasn't really a concern either. So maybe that made sense in a historical perspective when these networks were entirely separate. And availability absolutely had to be the most important thing. You can't really allow your water treatment plant for your city to go down, or your power grid to go down, or your rail switching network. So those historical priorities absolutely made sense. They make less sense in the hyper-connected world of today. So these legacy operational technology infrastructures, they haven't really fully adapted to the ubiquitous connectivity of, you can call it the modern internet, you can call it Industry 4.0, whatever you want to call it. A lot of these legacy systems that didn't really prioritize the confidentiality and integrity portions of information security, they're certainly feeling the pain. So when we talk about intrusion detection strategies and how these different types of environments are able to effectively perform intrusion detection, all strategies for intrusion detection really break down into three major categories, and that's going to be signature-based, threshold-based, and behavior-based. So signature-based, you're probably the most familiar with. It's the antivirus program or the anti-malware program that runs on your laptop, your smartphone, your home computer, etc. And that works really well in traditional IT networks. They're very homogeneous. It's not like we have 1,000 different types of operating systems that we run on our laptops or our smartphones. So signature-based threat detection works really well in environments like that. And it's easy for the people that operate IT networks to understand because there's a long history, reasonably good, false positive and false negative rates. Still not perfect, but reasonably good. Threshold-based detection, much more popular on the operational technology side, and largely that's because the people running these operational technology networks, they're mechanical engineers, they're industrial electricians, they're working with physical infrastructure. And so threshold-based threat detections are things like, are my compressors running at too high of a pressure? Do my pumps turn on too many times in an hour and are exceeding their duty cycles? Are the temperatures getting too high, which may indicate that the system needs to be serviced, lubricated, maintained, etc.? And finally, behavior-based. Behavior-based tends to be where we as researchers like to do all of our investigations. As researchers, we think, oh, we just need a better data set. We just need a thorough machine learning model where we can ingest all of this traffic from both the cyber components of these IIoT systems and from the physical components, chew on it all in a machine learning model, and we can spit out a unified threat model that encompasses both the cyber and the physical side of these environments. Industry's not yet on side with that, which is one of the largest problems that we do have right now. All of the research is focusing on behavior-based solutions, while the people operating the IT networks, they're heavily slanted towards signature-based. The people running the operational technology networks, heavily slanted towards threshold-based threat detection, largely for historical inertia reasons. That's what they know the best, and the point solutions that exist for each of those different threat models, they're well understood. There's a lot of different vendors providing solutions to those particular problems. So we end up with point solutions where we have one threat detection model for the IT side of an IIoT environment, and we have another threat detection system for the physical side. Working on a unified model is something that it's been elusive so far, and it's one of the challenges that I'm trying to address. So the reasons we haven't gotten there yet is the operational technology side have different challenges, different priorities. So a false positive or a false negative on an IT network might mean that you can't open a file on a computer, but it's fairly easy to roll back. A false positive on an operational technology network, that's got a much higher cost of failure. You don't want to shut down your power grid because of a false positive or a false negative in your threat detection system. On the OT side, we're also lacking in standardized communication protocols. IT networks, they've long since all gone to Internet Protocol. Operational networks, we still have a bunch of legacy serial-based communication protocols, none of them that were built with security in mind. So encryption typically doesn't exist on these industrial protocols. And the installed base, the lifespan of these systems isn't just 6 months or a year or 2 or 5 years. The power grid in your cities probably was installed 40 years ago, 50 years ago, and it's got a lifespan measured in decades. So swapping these systems out just because they were built in a kinder, gentler age where they weren't exposed to threats constantly, financially just isn't realistic. And so organizations that run these industrial networks just aren't doing it. And finally, it's really hard to test upgrades, patches, fixes on a live physical system. In IT environments, we spin up a virtualized test environment, we run our patches on it, everything is great, then we roll it out to production, no worries. On a physical network, it's not like you have a second water treatment plant or a second power grid that you can test updates on before you roll it out live. Those test beds just don't exist. We're getting a little better as virtualization technologies increase to have small-scale pilot systems or virtual test beds that we can do validation on for different types of threat detection, threat prevention. But it is slow going, largely because these systems, they live for decades. And that's largely what I'm working on as part of my research, is how to get those legacy OT systems talking using standardized protocols with built-in encryption, things that we can integrate, authentication, authorization, non-deniability into communication on both the IT side and the network side. I'm not the only one. There's a lot of international organizations that are working on coming up with standardized minimum security baselines, but it's slow going. And testing or parallel networks for validating updates, it's coming, but it's slow. And there's very little of this happening out in industry. Most of the virtualized test beds for industrial network testing, most of that is happening in academia. There's limited take-up in industry. So it's an ongoing challenge that we're working on. So fundamentally what I'm working on at the moment is a hybrid threat detection or intrusion detection system that works with the best of breed from each of those different strategies. So on the IT network side, using signature-based intrusion detection methodologies. Everyone understands it, they like using it, they prefer using it. And bringing in the OT side, essentially bringing the OT networks up to speed or letting them play catch up with the IT networks, because honestly that's where most of the intrusion detection engines come from. And integrating machine learning, just because some of these large sensor networks, they're simply too large to address with anything other than AI or big data learning models, just because it's overwhelming for humans. It's overwhelming for humans to process. So we need some sort of AI to separate the signal from the noise, just because there's too many false positives for humans to chase. So there's some promising work in eliminating the false positives from the amount of noise that we have in intrusion detection systems, specifically on the OT side. So that is a brief summary of what I am working on. So I'm going to open the floor up to any questions or comments that you might have.
Any questions, comments?
Thank you very much. I really enjoyed your presentation, because I deliver a subject in a cybersecurity master where I explain students things as you are collecting. And I have a question about the strategies. You said that you are planning in future works to use sensor data to gather, I guess, some information that led a machine learning based model to detect some kind of intrusion. Do you know exactly, or do you have you think in what kind of information are you going to gather?
So there's a lot of, I'm going to speak in very preliminary terms because I am working on this, but I don't think it's in a form ready for presentation. But in very general terms, there's a lot of promising work in machine learning, not specifically for intrusion detection, but for financial reasons. Organizations have been using AI to analyze sensor readings specifically for preventative maintenance. Because often these systems that a large, say, smart manufacturing plant might have thousands, tens of thousands, hundreds of thousands of physical components, valves, actuators, rotors, etc. And there are sensor readings that are coming off of these systems pretty close to real time. Frequently what happens is these components are not on a preventative maintenance schedule. So a rotor gets swapped out when it fails. A pump or a valve gets swapped out when it starts losing pressure or it starts leaking. Organizations have figured out that that rich amount of sensor data that's coming off of the physical components in their cyber physical systems can be used to predict when a rotor, a valve, a pump, etc., is going to fail. So to answer your question in a roundabout way, there is promising work on feeding all of this sensor data into machine learning models, not specifically with the goal of intrusion detection, but the goal of failure prediction. And similar algorithms can also be used for anomaly detection, specifically around intrusions. So with sufficient amount of sensor data, we can generate a model of what normal activity looks like, and we do binary classification saying this particular sensor reading is normal, or this particular sensor reading is abnormal, therefore potentially a threat. So I hope that answers your question.
Thank you. Any other?
Thank you, Professor. See, I would like to ask you about, do you think that blockchain technology could be a good intervention for these kind of systems? Are you using something like that?
There is a small amount of blockchain technology being used in this space, but it was almost so small in my literature analysis that it was essentially a rounding error. And the reason behind that is when you're looking for things like intrusion detection, most of it is log analysis or sensor analysis. The idea of having a validated ledger, it's not really a pain point for organizations for this particular problem. If it was things like power grids that are selling power at different rates depending on demand, absolutely. Huge demand for blockchain in that area because a distributed ledger that is going to multiple customers of power grid absolutely makes sense. I have not seen much in the way of demand for having the use of blockchain for maintaining things like which is essentially logging data that doesn't need to be shared with multiple parties. So blockchain really shines with sharing that data with multiple parties in a validated and verifiable way, which isn't really a consideration in this particular problem space.
And another one, if I may. See, what's the role of the big companies in the standardization of these protocols and everything? Because I assume there are participating.
There are. So there are a number of governmental and international organizations involved in setting these standards. So the big ones in North America, it's the National Institute of Standards and Technology. Everyone is probably familiar with them. They design encryption protocols, weights and measures, etc. Very common. In Europe, the largest organization managing that, it's the EU. So the European Union, they're largely in agreement with NIST on the North American side, and transnationally or transcontinentally, the NATO alliance, because NATO has got different national partners from both sides of the Atlantic. So those are the three largest international organizations that are working on these. From the industry side, industry sometimes moves a lot faster than government. So on the industry side, they're big companies, you've heard of them. ExxonMobil is one of the leaders. Schneider Electric out of Germany, Siemens also out of Germany, are the three largest on the industry side that are driving standardization, because these companies all want their products to work together, and these companies all have complex interrelated partnerships with each other. And so ExxonMobil wants their products to be able to talk to Siemens products, and wants to be able to talk to Volvo, and wants to be able to talk to Northrop Grumman. So those are the three biggest partners that are driving innovation in this space. And then there's 1,000 small companies that are just following exactly what the big guys do.
Thank you very much.
Thank you. Anything more? No? Well, thank you, Professor José.